And just a couple of announcements. You might have already seen this on Canvas. The last homework for the course is posted. It's a bit shorter and I hope a bit easier than the previous homework, so it shouldn't take a lot of time. You can submit it by December 8th or earlier if you want feedback on the homework before the exam. If you submit it by Monday, in particular by December 6th, we'll try to grade it and give it back to you in a couple of days so that you have it back before the final. The final exam will be available starting December 7th, which is Tuesday, and you can submit it anytime before 11:59 p.m. on Saturday. The format is the same as the midterm. You can start at any point. Once you start, you'll have 6 hours to finish. The length of the exam should be roughly the same as the midterm. So more or less what you already saw in terms of the format. Any questions?
Yes, I have one. Does the final exam cover the topics that the midterm did as well, or just the probability?
Okay, thanks. It covers all topics that we have discussed in course with a greater emphasis on probability, but we will also have problems related to linear algebra.
Okay, thank you.
Can skip the discussion on iterative solvers for linear equations. That was maybe a slightly more advanced application. I won't ask you about it in the exam. And you can skip the second half of the next lecture, or good part of the next lecture. We'll cover some we'll cover some application of continuous random variables in the next lecture, and then maybe I'll talk about a few generalizations, etc., which we won't need to worry about for the exam. Okay, so I'll mention this next time anyway. All right. Going back to what we were discussing in the previous lecture, let me remind you, since it's been more than a week, we started talking about defining various concepts and probability for the case of infinite probability spaces, and more so importantly, uncountable probability spaces. So, and we saw that what we need to give up is the notion of probability for every outcome of the outcome space. We can still talk about subsets of outcomes, which are events, and what we deal with is some kind of collection of allowed events or allowed subsets that we can talk about, and we define kind of a nice collection of allowed events which satisfy some natural properties that if we can talk about an event, we can talk about its complement. If we talk about two events, we can talk about their union, or in fact even countable collections. And the probabilities behave in the way we expect, that the probability of the complement is 1 minus the probability of an event, and the probability for a disjoint union of events, so the probabilities add up. And this allowed collection we called a sigma algebra, and an assignment of probabilities to these allowed events we called a probability measure. So the probability measure is now no longer a function from the outcome space to real numbers or positive real numbers, but rather it's a function from subsets of the outcome space or from the sigma algebra to positive real numbers, in particular the interval 0 to 1, because the probabilities of any event are numbers between 0 and 1. Okay. And then we saw that we can define things which we think of as natural objects, things like the uniform distribution on the interval 0 to 1. But because this is really an uncountable set, we have to be a little careful with, and so the correct way to define it is to say we have some sigma algebra, which lets us talk about this kind of natural events that we are interested in, and natural events are at least the sets of all subintervals, so interval from A to B, and then also kind of unions of intervals, and then by sort of complementing things, we also get get intersections, etc. And this collection of events or the sigma algebra generated by these subsets of 0 to 1, which correspond to subsets of intervals, which correspond to subsets like intervals and their intersections and so on, is what's called the Borel sigma algebra. And there is a probability measure here, which is called the Lebesgue measure. The Lebesgue measure is kind of more generally defined on the real space. There, it need not be bounded between 0 and 1. It's just a measure in general is an assignment from kind of sigma algebra to positive real numbers. When you really want things to kind of add up to 1, that's when we have a probability measure. And Borel sigma algebra, again, is a valid collection of subsets for the interval 0 to 1. You can also construct this for the real line or R2 or R2, R3, or in general d-dimensional real space. And instead of intervals, we'll talk of boxes that maybe the first coordinate is between A and B, and the second coordinate is between C and D, and so on and so forth. So this kind of objects exist for nice uncountable spaces that we often deal with, but to formally define things, we have to remember that when we are really saying we have a probability distribution over the interval 0 to 1, the uniform distribution, what we are really saying is that we have a probability measure which maps the Borel sigma algebra and assigns and sort of any interval A to B according to its Lebesgue measure. And these are just some things which I'm not really covering in a lot of detail. There are some resources linked from the course webpage. In particular, there is a course taught by Terry Tao on Foundations of Probability. There's also some excellent books which cover this subject in much more detail, entire books on this subject. So, well, just to sort of say that there are some things one need to be careful about when trying to define things over uncountable spaces. Okay. Any questions? This is sort of mostly what we talked about last time. Any questions before we proceed? Okay. Maybe not. All right. Now let's continue this sort of exercise of defining objects that we have already maybe seen in the finite case, and try to sort of figure out what's it's a good way of trying to define them in the uncountable setting. So the next object I want to talk about is a random variable. And recall that in the finite setting, we said a random variable is a function from the outcome space to, let's say, the real numbers. If the random variable is real valued, we said that there are also, you can define random variables taking space, taking values in any space. There could be vectors in R2, R3. They could be taking values over a finite field, whatever you want, except that when you're really writing sort of things like expectation of a random variable, then you better have random variables where you can multiply the values by probabilities and add things up. So reals or R2 or R3 are convenient, or like in general, any vector space which is over the reals is convenient. But yeah, you can think of more general spaces in which random variables can take values. Okay. Going back, let's just think of random variables taking values over the reals. And let's try to see what's an issue with trying to define this or trying to extend this to uncountably infinite spaces. So let's say we still have random variable as a function from the outcome space to say real numbers. Okay. And now it's a real number, so I can reasonably ask a question about it, such as what's the probability this random variable takes values between A and B? This is an event. Because it's a subset of omega. So X is a function. And so what we are talking about is if we are looking at the interval A to B, then what are the subset of values or what are subset of outcomes such that X maps this to points in this interval. So this is just the inverse of the pre-image of this interval A to B. Okay. Any issues with trying to calculate this probability? First of all, any questions about the fact that X being in the interval A to B is an event, when by event we mean a subset of omega. And in particular, this is the subset that we are talking about. Okay. It is a subset, but as we saw, when we are trying to work with uncountable spaces, we are not allowed to talk about all subsets. So a probability space comes equipped with a sigma algebra. And what the only events we can or we have well-defined probabilities for are events or subsets which belong to this sigma algebra. So we better have the fact that the event we are talking about better belong to this set of allowed events that we can talk about, or this sigma algebra or family of allowed events that we can talk about. So we have kind of a restriction on our function. We can't just talk of any function. We have to sort of make sure that our functions are such that any event of this form that we are interested in, which is, let's say, the probability of X being in some interval, belongs to the sigma algebra. Why interval? Well, okay. More generally, we think of a sigma algebra or a set of allowed events or set of allowed subsets for the values of this random variable that we are talking about. Okay. And let's say these form a sigma algebra f prime in whatever is the space in which the random variable is taking values, let's say the reals. So, and we saw a natural sigma algebra we work with in the space of reals is collections of intervals and things generated by them using the rules that we saw, which are just union and sort of complement and hence intersection, etc. So what we need to make sure is that if I have any allowed subset of values that I can talk about, then the probability of the random variable being in that subset, so that corresponds to the event, which is just the inverse of that subset, should also be an allowed event. So if I have any subset A prime here, and I ask, what is the chance that X lands inside A prime? Well, it will correspond to some bunch of outcomes here. And this should be an allowed event. So for every A prime, which is an allowed subset in the sigma algebra in the space of values, the set of outcomes which correspond to these values should be an allowed subset in the sigma algebra in the probability space. And such kind of functions are called measurable functions. They are measurable functions from the space omega with sigma algebra script f to the space of real numbers with the sigma algebra script f prime. The script f prime will usually be the Borel sigma algebra. But what we need to now say is that random variable is not just a function from the outcome space to whatever is the space of values, say reals, but it's a measurable function from the space of outcomes to reals, let's say in this case, okay, with sigma algebras on both sides also stated to properly define measurability. So we have to be a little more careful in terms of what a random variable is. Again, most natural examples we will see satisfy these properties. These are relatively natural properties once you work with the correct sigma algebras on both sides. But it's just to kind of point out that the notion of random variable just as a function does need an update when we try to work with sigma algebras. So we can't really talk of all subsets of omega. Any questions before we proceed?
Really quickly, is f prime, is that from the real numbers or?
So f prime, yeah, it's a sigma algebra in whatever is the space. So f prime is some collection of subsets of the real numbers. And it's again a collection satisfying all the properties of a sigma algebra. So it's a collection satisfying these properties. And most of the time we will be just working with well, there's not too much time left in the course, but in general, in most applications, you'll be working with Borel sigma algebra, which is just any interval is an allowed subset. You can talk about any interval and kind of natural subsets that you can form by unions, intersections, and complements of intervals. So F prime, you can just think of as a collection of subsets which includes all intervals and kind of natural operations done on them. Is that
okay? Yeah. Thank you. Thank you.
Right. Any other questions? Right. So this is just a recap of what I said. And more generally, there's nothing special about the reals. You can sort of define measurable functions for any space any kind of range space for this function. Doesn't have to be real numbers. It can be R2, in which case you will talk of the sigma algebra generated by or including all kinds of boxes, and or any arbitrary space, as long as you have a sigma algebra F prime on that space. What we will really need is that whenever you have an allowed subset of values, the set of points for which you get these values is an allowed subset of the domain. So whenever I have allowed subset of values, I should be able to talk about the event that X takes a value in this allowed subset. And these are all the points in omega for which X takes a value in this allowed subset. So this better be an allowed event. Okay. And that's more abstractly the definition of a measurable function. Okay. Any questions? Okay. Let's say you have x1 and x2 which are measurable functions. With respect to the same sigma algebra on both sides, here you can always think of the Borel sigma algebra when we are talking about real numbers. So just intervals as are your subsets of interest. Then check that linear combinations are fine, and in particular x1 c1 x1 plus c2 x2 is also a measurable function. Okay. Any questions before we proceed? So as I said, we will not be able to go into too much depth into all these notions and so what all issues come up, but I wanted to at least mention some of the key things that do come up, and in case you want to look them up on your own, or at least to kind of point out that some care is required when you try to define probability correctly over uncountable spaces. But unfortunately, a detailed treatment of this subject is a course in itself. Okay. Going forward, the next thing we talked about was a random variable. We defined its expectation. Okay. And now, any suggestions on how should we define an expectation for a random variable X? Let's say it's taking values over real numbers. So we can add values, we can multiply these values, X of omega by probabilities if we want to. How should we, or any ideas for defining expectations?
Maybe naively, this kind of seems like a case for like an integral over the function, or over the, an integral of the function over the interval.
Okay, yeah, so over a function over what, sorry?
A function over, I suppose, the interval that we're measuring it on.
Right, so, okay. So it's natural to think that, okay, when you're going to uncountable spaces, maybe the right extension of a summation is an integral. The problem is it's a little tricky to figure out an integral over what, because x is a random variable or x is a function defined on all of omega. So we may want to define an integral on all of omega, but then we can't quite write down nu of omega, and we don't, so can't write down this expression because now nu is not defined for every outcome. It's only defined for subsets of outcomes and some allowed subsets, but we can't quite define it for every single outcome. So this is a bit problematic. What you can define is, I mean, this is more of a notation than really an explanation, but in general, what you define is an integral of x, but with respect to this measure nu, and I'm not I'm not explaining what this means or what does it mean to, so going back to our definition of integral, what does it mean that we are integrating a function? Well, we kind of think of it as area under the curve, or whatever notion of integral you are familiar with, maybe thinking of maybe some approximation of the function and taking the sort of quality of the approximation to be sort of better and better, and discretizing it into finer and finer subintervals, the real line. And what you're really doing is kind of integrating a function and multiplying the value here by the size of this interval. And so if this interval is between a and b, then you multiply this by b minus a, and then you kind of keep repeating. This is what is called we call the Lebesgue integral. And this is really the integral with respect to the Lebesgue measure, because, well, we're not really taking the value of the function at a point. We are really taking it over a subset, and these subsets are intervals, and we are multiplying this value, which we kind of think of as fixed over this subset, by the size of this subset, or the measure of this subset, which is b minus a according to the Lebesgue measure. More generally, to do this correctly, you have to define integral with respect to a given probability measure nu. This, again, can be done. It requires some care, and will not develop it in full generality. I'm just trying to point out that it's non-trivial to define expectation when you have a random variable defined with respect to an arbitrary probability measure. So we'll cheat, and the way we'll cheat is kind of restricting ourselves to a smaller class of random variables, which are easier to deal with, where we can just basically get away by just taking our usual notion of integration or Lebesgue measure and just working with it, and not really bothering about all these issues that come up in trying to define integral with respect to some funky measure. So before we go there, is it? I just want to convey that there is some issue in trying to properly generalize the notion of expectation, or trying, because it's not obvious how to define the kind of integral we want. I mean, without knowing what the right definition is it at least okay that there is some issue in trying to find the definition? All right, let's continue. So a kind of nice class of random variables for which we can get around this issue is what are called continuous random variables. So let's say, and we can work with a slightly more general setting, but let's start with a random variable which is defined, let's say, from reals to reals, or the outcome space and itself thinking of as reals. And on both sides, let's say I have the Borel sigma algebra. So I'm going to talk about intervals or unions of intervals on both sides as allowed subsets. Okay. And then let me look at these kind of special kinds of intervals, which are intervals from -infinity to x. You can check that this will be an allowed interval in the Borel sigma algebra, so I can talk about the probability of this interval. And let me define now a function capital F of x, which is just the probability of the interval -infinity to x. Okay. This is sometimes referred to as the cumulative density function of the random variable x, which is just the probability that it's of the random variable capital X, which is just the probability that the random variable is less than equal to little x. And if it so happens that there exists a function little f, such that the function capital F can be written as just the integral of little f. Okay. And again, we'll see an example, but this sort of thing is also true for lots of nice random variables. Then we will call x to be a continuous random variable. So basically, the cumulative density function you can check is a continuous function, at least from one side. And if it's, in addition to that, if it's really a differentiable function, so it's nice in the sense it can be written as an integral of little f, then we will call x to be a continuous random variable. And in that case, we can write expectation of f or expectation of x as just the integral, not of nu, but of this function little f And when I say dx, I really mean that this is the usual notion of integral. So this is integral with respect to the Lebesgue measure. And I'm really thinking of the probability that that x is in the interval little x and little x plus dx. And this is not a formal statement, but this is kind of roughly how we are going to think of the integral. Is f of x times dx. So f of x is what we call the density function for this random variable. And so random variables for which we do have a density function, we will call them continuous random variables. This is not all random variables, but this is a subclass. It's a nice subclass, which is often convenient to work with, but I just wanted to emphasize that this is not all of them. And the random variable, I mean, it need not be random variables which take values in reals. It could be random variables which take values in r square or r to the d, and more generally, and we'll see examples. But if you can write the probability of being in an interval, or more generally in a box, as an integral of some function over that box according to the Lebesgue measure, then we will call this random variable x as a continuous random variable. And these are much nicer to work with. For these, we can easily define an expectation. And most treatment of probability over infinite spaces, we will be dealing with continuous random variables. And actually, I'll mention one example, which we'll talk about for the rest of the lecture. But I just wanted to give you a brief idea that trying to define probability correctly requires addressing some issues or taking some care. And it's not that all these things about density, which we usually work with for continuous random variables, it's not that these are just the only way random variables can be created. They're just convenient ways. Any questions before we get to a specific example? Okay. Now, I'll spend the rest of the lecture on one specific kind of continuous random variable, which is called the Gaussian random variable, or it's a normal random variable, or normal distribution rather, which refers to the distribution of this random variable. And this is often something that you see depicted by kind of a bell curve, although we'll see sort of a more precise definition in a minute. I mean, for reasons we'll talk a little bit over this lecture, and to some extent over the next lecture, it arises in several applications. It's fairly and the properties of this are kind of fairly useful to study. Before we get down to those, let me at least give you a definition. So it's a continuous random variable, which means that I can, and it's a real valued random variable. So let me tell you its density function. Using the density function, we can calculate the probability that it lies in any interval. So it tells us everything we need to know. It tells us the probability of all interesting events, which are just intervals or sort of unions, intersections, etc. So it tells us all the interesting probabilities we may need to compute about this random variable. Okay. It's usually denoted as n mu sigma square, where mu is the mean of this random variable. And this is the variance. Sigma squared is the variance. So sigma is standard deviation, which is just the square root of the variance. And the density is completely determined by this. So it's not something that is true for all kinds of random variables, but for Gaussian random variables, a real valued, which is often also called a one-dimensional Gaussian random variable, and we'll see multidimensional ones in a bit. Once I tell you its mean and variance, it's completely specified. There is nothing more to say. You can write down its density function from which you can compute everything that you are interested in about it. Okay. So let me write down its density function. First, let's say for a Gaussian random variable with mean 0 and variance 1. And this is particularly sort of clean and useful for a reason we'll see in a minute. The density function is sometimes denoted as gamma, and gamma of x is given by the function e to the minus x squared divided by 2 whole divided by square root of 2 pi. And more generally here, the density function is given by e to the minus x minus mu whole squared. And we'll, sorry. We'll play with these expressions for for a while until hopefully they appear a little more, until you feel maybe a little more comfortable with these. But there are few strange things about them. One, we have this kind of x squared in the exponent. There's this strange square root 2 pi sitting in the denominator. But it's some function. It's and since I'm claiming that this is the density function, what we do know is that if I wanted to calculate the probability of x being in the interval minus infinity to a, by definition of the density function, I can write it as the integral of gamma x. And by taking the difference of two intervals, which is really is the intersection of the complement of one interval with the other interval, you can say that the probability x is in the interval a to b can be computed as So for any interval, we can study what is the probability that x lies in that interval. If we know the density function for this random variable, and for the Gaussians, I wrote down some density function. Maybe it looks nice to you, maybe not, but at least we can calculate these probabilities. I mean, how to compute these integrals is another matter, but at least there is a recipe for calculating things. Any questions before we proceed? Sorry, Kyle, were you trying to ask a question?
No, I think I'm okay. I think I'm okay. Thank you, though.
All right, so let's explore this crazy function a little more. One, I kind of owe you an explanation for this, at least for this strange square root 2 pi that appears in the denominator, and that actually comes from a sort of necessary requirement that the probability that the random variable lies between minus infinity and infinity should be 1. Because it's a real valued random variable, so it has to lie somewhere on the real line. And so the probability of this event, which is the entire real line, should be 1. And so if we sort of calculate or try to calculate the value of this integral, which is just without any normalization, just the number e to the minus x squared divided by 2, we'll check in a minute that this is equal to square root 2 pi. So we divide this number by square root 2 pi so that the integral is 1, and then the probability of the real line is 1. And that's where the 2 pi comes from. If you haven't seen a computation of this integral, it's one of those things that you should see at least once. It's kind of a nice computation, and it's not too involved, but it's maybe a slightly different computation than what we do most of the time. So I'll do this in 2 steps. Let me go to the second step first, and then we'll come back to something which we kind of actually need along the way. But I claim that square of the integral is 2 pi, and to think of the square of the integral, we can do it in terms of 2 variables. So okay, let me do it more slowly. And I want to write it as actually a double integral. And to be fair, this step needs the fact that the integral is bounded. I'm using really so-called Fobini's theorem, which lets me switch the order of the integral to write this double integral. So to be completely correct, I need to show that the I is bounded before I can do this. But suppose we assume that, then instead of thinking, so x, y are points in the 2-dimensional plane, and instead of thinking of them, instead of using the coordinate system of x and y, we can think of polar coordinates to do the same integral. Once you sort of think in terms of r and theta, again, it requires maybe a little bit of computation, but if you have a point x, y, then the radius is just x, so r square is x square plus y square. And you can check that dx dy will become r dr d theta. And yeah, you can kind of derive it in various ways. You can either sort of recall your definition of a Jacobian, or just think of what an area of a small element is, which is kind of the maybe the less formal way of doing the same thing. And then we can kind of do the integration over theta first, because there is nothing which really depends on theta in the expression. So we get 2 pi times integral of e to the minus r square over 2r dr. And then maybe after a change of variables, you can check that this is equal to 1. Just plug in r dr as y, you have e to the minus y, and then r is going from 0 to infinity. So that's maybe a sketchy proof in more than one ways. But yeah, you can make all of these steps somewhat formal. And it's easy to check that the integral is bounded. This is the kind of approximation we do many times to sort of understand integrals. So you can think of instead of going from minus infinity to infinity, you can think of going from 0 to infinity. And this is a common technique we use to show expectations of various things are bounded. Just break the integral into two convenience parts where you can use different bounds. So let's say I break the integral, and you'll see why the choice of 2 in a minute, but and 0 to 2, you can just say that this is less than equal to 1. So this whole thing is less than equal to 2. In this part, you can use the fact that e to the minus x squared is less than equal to e to the minus x when x is greater than equal to 2. So therefore, the whole integral you can check is less than equal to e to the minus 2. So it's some bound, but it's just bounding it by a function which you know how to integrate. And so as long as we can obtain some finite bound, we can actually compute the value precisely using the manipulations in the next step. Okay, that's just again an explanation for where this 2 pi comes from in the expressions for their density functions. So at least the square root 2 pi in the denominator makes sense because the numerator integrates to square root 2 pi and we want the whole thing to integrate to 1 actually. So we just normalize. Okay. Another thing which, and the x square is kind of nice, as we saw that when we were trying to integrate x square and y square, we kind of had x square plus y square add up in terms of r square. And this kind of shows up in a nicer way when we try to think of multiple Gaussians at the same time, which also gives it some nice properties. But before going there, let's just formalize what we mean by two random variables. So of course, we can think of two functions, and we will, as before, we thought of random variables as independent if the event that one random variable takes one value and the other random variable takes some other value are independent events for all values. And again, because we are working with uncountable spaces, values will be replaced by allowed subsets of values, which in this case would be intervals. So what we want is that for all kind of boxes which are given by A and B on one axis and C and D on the other axis, we want the probability to be equal to the product of the probabilities. And now let's say this random variable has a density function . And let's say this has a density function G. So we can compute these probabilities. And again, because both these integrals are bounded, we can really think of it as okay. And You can think of this in two ways. You can either think of it as a product of probabilities, or you can think of it as a density function for the random variable which is given by x comma y, which takes values in the space R square. And so we can specify multiple independent random variables, or more generally, in fact, we'll see not necessarily independent random variables by thinking of a random variable which takes values not as real numbers, but as tuples of real numbers or a vector of real numbers. And we will give a density for vectors, a density function for vectors. So these are two common ways in which we can think of multiple random variables at the same time. And in particular, for independent random variables, it's relatively simple. For Gaussians, we'll be dealing with independent random variables in the course also, although I'll kind of mention some things which are useful to keep in mind when you don't have independence. Okay. Going back, let's get to the case of multiple Gaussians. Let's say we have two Gaussians. Okay. And here, something very nice happens, that if you have, let's say, two independent Gaussians, let's say both of them have mean 0, variance 1, and this is again the most common setting, and we'll see why in a minute. Then so if you take a linear combination of these two Gaussians, let's say coefficient C1 for x1, C2 for x2, then this linear combination itself is a Gaussian. So it's a Gaussian random variable with mean which is also 0, and variance which is C1 square plus C2 square. Okay. And similarly, if you a random variable which is a Gaussian, and you, let's say, take a linear combination in the sense you just sort of scale it by something and add a number mu, then expectation of this new random variable by linearity of expectation will be mu, but it will actually be a Gaussian with mean mu. And the variance will be dependent only on the variance of x1. In this case, it was 1. We multiplied it by C1, and we will get C1 squared. So these are facts to prove. It's not entirely clear that these strange things give us Gaussians. But these are nice properties that linear combinations of independent Gaussians give us Gaussian random variables. We'll say a little more about linear combinations of general Gaussians in a minute. Okay. But before we prove anything, notice that this property gives us a very nice way of thinking about a general Gaussian distribution. So let's say you have X, which is distributed according to the Gaussian distribution with mu and mu, variance sigma squared. Okay. And if you have Y, which is distributed with mean 0, variance 1. From what we just said, if I look at the random variable, which is a simple linear transformation of Y, or not quite linear, but in a fine transformation. So I multiply Y by sigma and add mu. Then this is a Gaussian distribution with mean mu and variance sigma square. So if I want to study a Gaussian random variable with mean mu, variance sigma square, I can just prove all my properties about mean 0, variance 1 Gaussian distributions, which is sometimes called a standard Gaussian or a standard normal random variable. And some sort of linearity of expectation or some linear transformations are enough to understand more general one-dimensional Gaussian random variables. So, which is why a lot of the time we'll just see properties proof for mean zero, variance one Gaussians are kind of cleaner to work with, and you can translate the results to more general ones just by sort of using some linearity properties. Okay. Going back, a proof of this fact. Okay, let's see if we come back to it. I may not. I want to say some other things, so I'll not get into the proof right now. But it's actually, I mean, there are multiple proofs of this fact. One is just by computing the density function. So we'll get to that in a minute. But let me point out that if we don't have independence, then this may not be true. Then not only can we sort of not necessarily compute the variance, but we have to be careful if the linear combination is a Gaussian or not. So here's an example. So okay, let's say x1 is a standard Gaussian random variable, and let's say x2 is equal to x1 if absolute value of x1 is less than equal to 1, and it's equal to negative x1 if the absolute value of x1 is greater than 1. You can check that the density function for x1, of course, is a standard Gaussian, we just said. You can check that x2 is also a standard Gaussian. They're not independent. x1, x2 are not independent. But what happens to x1 plus x2 is weirder. So here, x1 plus x2 is 2 times x1 if x1 is small, and 0 if x1 is larger than 1. So in particular, whatever we get as the random variable x1 plus x2 is something which is always between 0 and 2. It never exceeds the value 2. And a Gaussian always kind of has this curve which goes off to infinity. So it's never bounded in any finite interval. How sharp this peak is might depend on the variance. Where this peak lies might depend on the mean, but it will always go off to infinity. So this is not a Gaussian. And this is a bit of a pathological case, but I just wanted to point out that we often say linear combinations of Gaussians are Gaussians, not just for independent ones, even for other Gaussians. So that requires an extra assumption, or that requires some extra property of these. So So an equivalent way of stating that linear combinations of x1 to xn are Gaussian random variables is to say that x1 to xn are jointly Gaussian. And usually when you are given a collection of Gaussian random variables, either when you say it's a Gaussian random vector, it implies that these are jointly Gaussian, and sort of in most cases, this assumption is implicit, if not explicit. But something like this is required. And so, for example, there is a sort of homework problem where we talk of something like this, but it just, and yeah, after this lecture, you should have everything you need to solve the homework problems. But I just wanted to point out that linear combinations of independent Gaussians will always give you Gaussian random variables. When you don't have independence, sort of almost always we have this assumption of the fact that these random variables are jointly Gaussian, but we do need it. And so mostly sort of when we define what is called a multivariate Gaussian, we actually mean that each coordinate, sort of we have a vector of variables, each coordinate is Gaussian, and these are jointly Gaussian. So any linear combination is also a Gaussian. And the most common case, again, is when these are independent, in which case things are easier, but there are many interesting examples where you don't have independence. So let's restrict to a subcase. So let's say each of these is just a standard Gaussian variable or the standard normal random variable. And let's assume that these are independent. So a shorthand for this is that X comes from the product distribution of the normal distribution. Okay. In this case, what we do get is that you can write a nice density function for this vector valued random variable. And this will be, again, because these are independent, it will just be the product of density functions. So it will be the square root 2 pi, which comes from each of them. And you can write it in a nice way, which is just the norm of this vector divided by 2 pi to the, where X is the vector consisting of x1 to xn. So interesting thing is this density function is only depends on the norm of the vector. So it doesn't depend on the direction in which the vector x points, as long as we know its length. And this is often referred to as spherically sort of a spherical symmetry property. So this density function, and hence the random variable, is spherically symmetric, which means that if we take the density function for any particular vector x, and rotate it or move it to any other point on the same sphere, so at the same distance from the origin, the density function will not change. Okay. And so the distribution of this n independent Gaussian random variables with, let's say, mean 0 for each, variance 1 for each, is a spherically symmetric distribution, this product distribution. And this is, again, a very useful fact for applications. It doesn't depend on which direction the vector is pointing in. It just depends on the length of the vector. Okay. And for that reason, sometimes you'll just see of this being referred to as a spherical Gaussian. And just like we can go from a general Gaussian random variable mean 0, variance 1, and sort of with some linear shifts, we can convert it into a Gaussian random variable with mean mu, variance sigma square. So it's sufficient to study, or it's okay to prove many properties for mean 0, variance 1, and then we can calculate them for more general settings. The same is true when you have a collection of or a multivariate Gaussian or a collection of coordinates which are jointly Gaussian, so that any linear combination is still a Gaussian. In that case, you can obtain this by some sort of natural operations done on a spherical Gaussian, although I won't necessarily get into those details. We'll prove some properties of spherical Gaussians, and yeah, that will be sufficient for the analysis we need. Okay. And let's just do a couple of simple computations, and then maybe I'll go back to the proof that I left out. Let's say we have X, which is a standard normal random variable or a standard Gaussian, which is given by this density function. Okay. And by what we already said, you can obtain the density function mean mu, variance sigma square. I mean, we already wrote down a formula for it, but you can actually derive it using the density function from a standard normal distribution. So based on what we said in terms of, and actually you might have used that in the proof. So suppose X is a standard normal random variable, or what is the expectation of X?
Is it 1?
Why is it 1?
That's the goal, or that was what we were focused on with the normalization. So like the integral, like we need the normalization of the integral to sum to 1. Okay,
good. So we know that gamma of X integral is 1, but that's not what the expectation is. The expectation of a random variable is X times gamma of X dx. This is 1. And this is what I'm asking for.
Zero.
Why is it 0?
Because the inner function x times gamma x is an odd function.
Right. So it's an odd function. And actually, I mean, yeah, I've been referring to this random variable X as a mean 0 random variable. I mean, I didn't prove it, but it better have that property if I've been calling it a mean 0 random variable. And what you said is exactly the proof. Whatever appears inside this integral is an odd function. And we are integrating from minus infinity to infinity, so the values will cancel out. 0. Actually, you also gave the proof that the expectation of x cube is 0, because if you replace little x by little x cube, it's still an odd function. What about expectation of x square?
1.
And why is that?
Variance is 1 as you defined it. So if you
Right. So we've also been calling it variance 1 random variable. So the variance better be 1. But if you want to actually derive it, you can also try to prove this. Also, although yeah, it might require a little bit of work, maybe a change of variable, maybe integration of by parts, or whichever is your favorite way of doing this kind of integral. Okay, so you can compute this and then check that this integral comes out to 1, and that's why I've also been calling it a variance 1 random variable. The interesting thing is, once you know these, you can compute, let's say x to the 4 or x to the 5 will be 0, x to the 6 you can compute, and so on. And there is in fact a formula for this, and you can find, and one of the homework problems actually derives this formula and gives something even more general. So I'll leave as an exercise, but it's once you know how to compute the first couple of integrals, you don't have to compute everything else by hand. You can sort of derive some nice expressions for these in terms of the first couple of integrals, and then I'll refer you to the homework for more details. Let me also try to compute this integral, which is something which wait, since my integral seems to have disappeared. Sorry. Okay. Let me try to compute this integral, which also illustrates manipulation we often do, and then this is something which we'll need in the next lecture. And in fact, it's sort of also used to define when some random variable, sort of how much it looks like a Gaussian, which is in some way of sort of defining Gaussian-like behavior for other random variables. So going back to this particular integral, e to the lambda x square is some other function, and so we can calculate its expectation just as we calculate the expectation of x squared or some sort of functions above. And we can plug in the value for, or the expression for gamma of x. And now there's something to notice. Okay. One thing to notice here is that if gamma is bigger than half, then the exponent is actually positive and the integral will go to infinity. So we can't really get a finite bound on it if gamma is bigger than half. So it only makes sense to try and obtain the value for it. Oh, sorry, not gamma, lambda. For lambda, which is less than half. And for lambda, which is less than half, it's easy to kind of relate it to the integrals we know for Gaussians by using a change of variables. So let's think of square root 1 minus 2 lambda x as y. And once we do this change of variable, we get that this is equal to because the rest of the part is just again the integral of the Gaussian density function, now written in terms of y, and we know that integral is 1. We just proved it earlier. So a lot of the time we end up using the fact that the integral of Gaussian density is 1, and we try to have something in the exponent which looks like e to the minus something square divided by 2, or try to complete a square in the exponent, in this case just by changing just by scaling y. What you need to do in this sort of that I left out is also just complete the square, but by a slightly different manipulation, and try to calculate the density function for C1x1 plus C2x2. You can try it, but otherwise ask me in the next lecture. I'll also include the proof in the notes. But these are just some examples of how to think about Gaussians or how to compute with Gaussians. This should be all what you need for the homework, and then we'll talk about some applications of these in the next lecture. I'll stop here. I'll stay on for a few minutes after the lecture in case you have any questions.